Right now, though, let's take a moment and summarize what we know about the two types of circuits. First off, let's look, since we did it first, let's look at series circuits. What does a series circuit look like?
Does that be like a circle?
Sort of like a circle, like a single loop. And usually we're going to draw it as more of a square because it allows us to be neater. But yeah, a single loop. So here's an example. We would always label the voltage of the battery and then the resistance of each resistor in there. And now we had three rules that we'll talk about for each circuit, one for voltage, one for current, one for resistance in the circuits. So let's start with the easiest one. What can you tell me about resistance in a series circuit? Yes?
You just add them all up.
Just add them all up. The sum of the individuals is equal to the total.
Oh yeah.
And that's because any electron leaving the battery has to go through all of the resistors to go back to the other end of the battery. They always want to go from negative to positive. And so it's experiencing all of those. What can you tell me about the currents here, Emily? Same everywhere. Same sort of reason. There's only that single path for electrons to go, so there's no place for them to branch off and maybe choose one path over another. So they have to keep going around. We also don't get bulges in the wire where there are extra electrons or anything like that. So electrons have to keep flowing around at an equal rate. So the current is the same everywhere. We would find that current by taking the voltage and dividing it by the total resistance using Ohm's law. And then finally, our voltage rule. What do we know about voltages in this? Yes.
Divided amongst the components.
It's divided up amongst the components. How do we know how much each component gets? How does it get divided? So this battery voltage, you're right, gets divided up amongst these. Which of those would have the most voltage dropped across it? What is voltage? Yes?
Two things. One, can I go out in the hallway to take the test?
No. And I asked you a question.
Yes. Voltage, is it's not the lack of moving, it's
Not the moving either.
the
Potential energy that pushes.
It's energy. Think of energy. So it's the push behind them, though. So maybe that's what you were getting at with this sort of weird. I don't know. It's how hard they're pushed. And so if we're measuring the voltage drop, we're saying across something the energy drops a little bit. It's being converted from electrical energy into heat energy usually along something. So which of these resistors do you think is going to convert the most amount of electrical energy into heat energy? Which is it going to take the most energy to get through? Don't want to alarm anyone, but you might all be doomed. The 15. the higher the resistance, the more energy it takes to push electrons through. So if we want to know how much voltage is dropped, we're going to go back to Ohm's law. We used it once on the whole circuit to find current, where we took the battery voltage, which is sort of like the total voltage, the total resistance that we found. We would find the total current, but that's the same everywhere. We'd go back and use it again now on one little piece. So if this current is the same everywhere, we know how much current is going through this. We could just take the current multiplied by the resistance to find out how much voltage is dropped across that one. Now, Emily had stated that the voltage is divided up amongst all of the components, but then the other part of that is when you add up the individual voltage drops, you're going to get the battery voltage back. So you can say it either way. I'll just say the battery voltage is divided amongst the components in the circuit, and how much they get depends on their resistance. Okay, so those are the rules for series circuits. Parallel circuits what do parallel circuits look like? More like a ladder, yeah, on the side. So if we start out with our battery, we'd have one rung there, add another rung, and we could go on and on. Let's label the battery voltage, label the resistor values. We had 3 rules with them too.
The voltage is the same throughout.
Same everywhere, because basically all of these are connected back just by wires. And the wires that we draw are perfect wires, so they don't use up any of that energy themselves. So the voltage is the same on all branches and battery. What do we know about currents in a parallel circuit?
The branch current adds up to the battery current?
Yep, because battery current comes out and then it goes through one of these branches. So if we add all of the branches up, we must also then be getting how much comes out of the battery. And then finally, our resistance rule, the one that often seems to make the least sense, Kevin.
All the resistance is smaller than the smallest resistance.
Right, you can't add it up anymore. If you take this total current, so the battery current, divide it by the battery voltage, you get a resistance that's a lot smaller than any of the individual branches. And that's the whole thing with having extra lines in the checkout lanes. Extra lines, even if they're slower, help move all of it along. The key to all of these is applying Ohm's law, either to the whole circuit all at once, which is okay, or to an individual component. But the trick is, don't mix them up. You can't use a total resistance and, well, here you could, but like a total resistance and a single current. Or you couldn't say, if this is our branch 3, you couldn't use the current flowing through branch 3 along with the resistance of branch 1. It won't work out that way. So you have to be careful to keep them separate. When you're talking series circuits, same thing applies. You need to know, you can't look at 10 volts being applied across the 10 ohms, because that's not what happens. The 10 volts is applied across the total. So you have to keep them separate like that, but otherwise it's just Ohm's law. So the math part is easy, the application of it is more challenging.